Hello, everyone. Nice to see so many people here in Kino One. So I'm not Hila, but I'm Julia, and like Martin said, I'm not a professional moderator, but I'm a web developer, and I like to bring you through the next 2 days safely. And I'm very excited that Hila Safi is our keynote speaker today, because I already met her a couple years ago during a Google Tech Ambassadors program. And since then, we've met in all kinds of cities all over Europe. And every time it was the same. She made all the super complicated topic so easy for me. She just did it like that, you know? We were having coffee or tea, whatever, and she just explained me the most, craziest things in easy words. And that's also what she's gonna do for us today with the topic quantum computing. So please give a warm welcome for Hila Safi.
Yeah, my name is Hila, and I want to talk to you about quantum computing. But I would like to get to know you first a little bit. So who here is in software development? Please raise your hands. Okay, that's good. Who works in systems development? Okay. Who has read up on quantum computing a little bit? Okay, cool. That's nice. Then, last question, who has seen The Big Bang Theory? That's also good. So I know a little bit about you, a little bit about myself. So my name is Hila. I also, by training, I'm a software developer, I'm a computer scientist, and then I stumbled into quantum computing. And when I started, it was just, I feel like we as developers, we have this tendency when someone asks us if we can develop something or code something, we just say yes. We never heard the term, but we just say yes. And that's how it happened with me. I was asked if I want to do something, combine AI and quantum computing to solve problems that are not classically solvable. And I was like, yeah, sure. And I thought I will just, look at my search engine later and then figure it out. But it was lots of ups and downs and lows and highs. And we're here today because I just want to help you to navigate through all of it, to understand where to start and where to stop if you want to start as a developer for quantum computing. So let's start our journey. I really love these maps. They're by Wellington. It's an online educator. And when we talk about quantum computing, we need to start at the physical level. So quantum computing is based off of quantum mechanics, and I think most of us are familiar with classical physics, right? It describes everything on the macroscopic level, everything that's visible to the eyes, like the laws of gravity, or how objects do motion under force, electromagnetism, and so on. Quantum physics describes the smallest things in our universe, down to cells, atoms, neutrons, electrons, molecules, and how they behave when they interact with light. And even though it kind of explains how the universe works, it is very counterintuitive for us. And that's why oftentimes you will read something like, oh, if you think you understand quantum mechanics, you don't really understand it. It's so complicated, no one gets it. And that's not entirely true, because we do understand it. We have used quantum technology for decades, really. And it actually would be quite dangerous if we didn't understand it, because nuclear plants, atomic bomb, MRI machines, lasers, all is based off of quantum mechanics. So why do people say statements like that? it's because we cannot visualize it, because it is the behavior of things that we cannot see. So one of the things that might be so counterintuitive that is a rule in quantum mechanics is that a particle can be a wave and a particle at the same time. So the closest thing in life that comes to it is like if you have a ball, a bouncy ball, and you drop it into a pond of water, and then you see that wave start. So it's like a particle and a wave at the same time. Something else that's very counterintuitive is that a quantum system can be in 2 or even more states at the same time. So something could spin to the right and to the left simultaneously. Now, I couldn't show you because I cannot do it, and you cannot imagine it. So that's what people actually mean when they say you cannot understand quantum mechanics. Mathematically, you can. And even like MRI machines, that's actually how they work. They look for the hydrogen atoms in your body and they spin it in both directions, and this is how we can actually do scans. So, just briefly, like I said, quantum mechanics started over 100 years ago. And then why the hype now? So there were like 2 little hype phases. So it started like in the 70s when some theorems came out that were the basis for quantum computing, which is one part of quantum technologies. And Feynman, who became the face of it, just said that, okay, a lot of things in the world are quantum systems. And I don't think that a classical computer can simulate a quantum system very well. So let's build a quantum computer that simulates a quantum system, which kind of makes sense. And then the race for creating algorithms began. But at that time, there was no quantum computer to test it on, maybe a 1-qubit machine, and that was about it. And then it kind of faded, the topic. It went like to the background, the quantum computing topic. And then it resurfaced when big companies started to build their quantum computers. And that's why we have a hype now, because we actually now have quantum computers to test all the theories. And today, like I said, I want to help you to navigate through if you want to enter to being a quantum computing developer, what to do. And we will start right at the top left with explaining what the difference between classical computing and quantum computing is. Sometimes you will hear it is a faster classical computer, but that's not true. It would be like comparing a light bulb to a candle, right? So both give lights, but it's an entirely different technology, so you cannot really compare it. So we will talk about that. And once we understand the difference between classical computers and quantum computers, we can then continue to understand, okay, so why they might be suitable to solve problems that we cannot solve classically today. I will also briefly talk about quantum hardware, because if you develop quantum software today at the stage that we have, you need to understand the underlying hardware. It's just like decades ago with classical computers when they just came out. You had to be aware of the underlying architecture. And in the end, to show you some of this phenomena and characteristics, I will show you a very, very, very quick code example and also make you understand how you can access quantum computers for maybe not so much money. So yes, let's start with the difference between quantum computers and classical computers. So the difference actually starts already at the CPU, QPU level. I think we're all aware classical computers have bits, and every bit can be either 0 or 1. In quantum computing, we have qubits. Cute, right? Just the Q at the front. So a qubit can be in a state of 0, 1, or in a linear combination of both states. So it can be 0 or 1 at the same time. This is due to the superposition that I talked about in the beginning. Something can spin in both directions at the same time. Then we have entanglement. So entanglement was something that was actually discovered really early on. Einstein Podolsky and Rosen wrote a paper on it, and they called it spooky interaction at a distance. So what it is basically, if you have two qubits interact with each other in the beginning, you can entangle them. And then you can entangle their state or the information that they carry, basically. And then you can just like spread them across any distance you would like. You can entangle 2, 3, 4, you can entangle multiple qubits. And these qubits remain entangled, no matter how far away they are from each other. They can be away from each other across space. This was actually also tested. And as soon as you have information on the one qubit that's still with you, you also have the information about all the other qubits. So that's why sometimes people talk about teleportation in the quantum space. So basically, you could teleport information from A to B faster than the speed of light, some say. But you still have to get the qubit to move across the distance, and that's not faster than the speed of light. And that's also the little bit dangerous thing about quantum computing, because some people take something that's like half true and make something crazy insane about it, when in reality it's just linear algebra. Measurements. Okay, once you're done with your calculations and you have all these qubits in superposition, at the end you want to read something that is a bit string, right? Because that's what we can work with in the real world. So you have to measure your qubits. You have to observe them and you have to look into it. And in order to measure the qubit, you kind of break the superposition state that you had before, and then you either have like 0 or 1. So what does that mean for information encoding? So it means that, let's say we have 2 bits, then we can represent one number between 0 and 3. And we can save the information of one number. If we have 10 bits, it's a number between 0 and 1023. With quantum computers, you can also represent with 2 qubits 4 numbers, 0 to 3, but you can represent all of those numbers simultaneously. So you don't have to choose between one number, but all of them. And yeah, Chris Monroe says with 300 qubits, you have more possibilities than there are particles in the universe. So this means that with very, very small numbers of particles, we can store and manipulate a vast amount of information. And if you look at penicillin, for example, you would need 10 to the power of 86 bits to represent penicillin, whereas you only need 286 qubits. So we have an advantage when it comes to storing information, but also when it comes to performing operations, right? So when you have your bits, then you add gates, and those gates do some operations or instructions. With quantum computing, it's the same thing. You have your quantum computings, you do the gates, and that performs operations. But with the classical computing, you can only perform the operation on a single bit at every step. With quantum computing, you use the superposition, you add the gate or the instruction to the entire superposition, and then you can basically do it on the entire search space at once. So that means you sort of have parallel operations on all the solutions due to the superposition and also entanglement. So you need less memory, you need less operations, which amounts to less energy consumption. Yeah, so an example for it would be, if we have the traveling salesman problem, we have some cities that we want to visit, we want to find the shortest path. With classical computing, this is brute force, I'm aware of it, you just try one after the other. There's better approximation algorithms today, but there's no algorithms for a high number of cities that could give you the exact best solution. So, whereas with classical computing, you would need n tries to find the optimal solution. With quantum computing, one go would be enough. So now when I want to show you one more thing. So this actually gives us the hope that we can solve these problems that are classically not solvable. So in classical computing, in order to understand how good your algorithm is, you can look at the space complexity, or you could also look at the time complexity, right? So how many steps does it take to finish my algorithm, and then the space complexity, how much memory I need. So we already learned that with quantum computing, we need less memory and less time to solve problems. So we have these classifications in classical computing of P and NP problems and NP hard, and we're not sure yet if P is NP, but we do know that NP problems are very difficult to solve or unsolvable when we look at the bigger picture. Then we have, of course, a different complexity classification for quantum computing as well. And BQP is the class of all the problems that we believe we can solve efficiently with the quantum computing. And we do believe that some of the problems in NP complete are also in that class. So this is sort of the motivations. So let's look at some applications. So we used to be in the theoretical realm for a long time, but now actually we are in the practical world. So there have been lots of first pilots. VW, for example, use it for several optimization problems, for example, for autonomous fleets. We optimize batteries with it. We even optimize energy consumptions in buildings with it. So these are like the first pilots, proof of concepts and trials. It is also used for better predictions when it comes to weather forecasting, power grid optimization, water utilization prediction. In finance is actually a huge platform for quantum computing applications, risk analysis, portfolio optimization, fraud detection. And KPMG's project actually on portfolio optimization showed that for near-term investments, the quantum computing algorithm actually performed better. For long-term investments, we don't have enough qubits to do that yet. But this is a nice indicator. When the hardware is better in the future, we could actually make much better predictions in finance. Logistics, we already saw like the route optimization works very well, but then also supply chain, stuff like job shop scheduling, because basically job shop scheduling can be mapped onto a traveling salesman problem, and you have the same mathematical formulation. In manufacturing, for designs, like nowadays, if you want to buy a car, you have millions of choices on how you want to build, you customize your car. So it's actually a very, very big optimization problems with millions and millions of variables, and classical computers are not really able to perform on it well. So IBM is working on optimization problems there, not just IBM. And then also simulation is a big part, simulation of materials, and the pharma industry. Like I said, a quantum computer, and this was like the initial idea, is able to simulate quantum systems and our bodies and drug interactions. It's all molecules. And if you could simulate it better, you could design better drugs. So yeah, to just like summarize it up, like optimization problems, we saw a bunch. Machine learning AI is actually something that I didn't mention in the first trials, but quantum computing, you could look at it two ways. You could use quantum computing in order to better your machine learning algorithms, because you can look at a bigger solution space, because you can encode more information, or you could also accelerate the training, because you can just try out different things faster. Or because today we have lots of challenges with our quantum computers, which we're going to get to in a minute, you could also use machine learning in order to help with some of the challenges that we have. Simulation, like it was intended to. A good example is like when you develop new materials, then you prototype it and then you try it out. With quantum computers, you could simulate that whole process, and what would take 6 months would then just be done in half a day. Cryptography might be like the first step into the quantum computing world, because people sometimes act out of fear, unfortunately. And yes, there is an algorithm that can break RSR encryption if we have enough qubits, but for that we need quantum computers without the challenges that we're going to talk about in a minute. So yes, this is a threat, this is a danger, but I think we have security dangers will always be there. And I think and believe that we will always find solutions to them, so I'm not too worried about that. And then there's also search algorithms. The second most famous algorithm in quantum computing ever developed was Grover's search, which gives you a 4 times speed up compared to classical search, but, and here's again the thing that's always exaggerated to hype something up, compared to brute force. It's still not bad to have a quadratic speed up, but there's also better classical algorithms in search. So yeah, we have different problem classes from chemistry to combinatorial optimization, and the expected speed up differs from exponential speed up to quadratic speed up. And depending on your use case, you just have to evaluate, is it worth the additional cost to use a quantum computer? I think for exponential speed up, definitely is. So let's look at some of the challenges, because it kind of sounds too good to be true, so why are we not using it? Quantum information is susceptible to disturbance, so any interference from the environment will break the superposition that we need to do all those fancy calculations. So if you go to a lab and you have a superposition particle and you just stomp on the floor, it will break the superposition. Similar to when you toss a coin, it's heads and tails at the same time, so it's sort of in a superposition. But if someone just comes too close to the table, or there's some vibration, the coin will fall before it is supposed to fall. And then the qubit quality. Qubits are dainty, they jump around, they're very difficult to control. And right now, our qubit quality is not the best. We have also lots of errors that happen due to noise, but also due to the qubits not having the best quality. And these errors are actually unknown to classical computing. That's why we cannot just take the error correction system that we have in place for classical computing. Also, quantum information cannot be copied, so we cannot just do a copy and then do a check if our calculations were correct. So to correct errors, we need to make more measurements, and to have one logical qubit, there are estimates going around from 1,000 to 100,000 qubits. So we'll see where we're headed to there. Just briefly, that quantum computation is so in the beginning that we have many different models. There's gate-based, there's quantum annealing. We will focus on gate-based. I just want to know that what you hear now is not the only type of quantum computer out there. There's many different ones. And we don't know where the future is headed to, what's going to prevail. Or maybe there's going to be different types of quantum computers for different types of problems. So let's look at the hardware. So we need a qubit. That qubit can be anything from an electron to atoms to ions to photons. And all of these qubits have different advantages and disadvantages. Then we need to manipulate our qubit. We're gate-based now, with adding gates. And in the physical level, you can do that with a laser, you can do that with temperature. Depending on what your qubit is, again, that changes. And they need to interact with each other. And you need to be able to measure them. If you're more interested about the quantum hardware, there is the Venshaw's criteria for a universal quantum computer. Like I said, all platforms had advantages and disadvantages. Some you need to cool down very much. Some are very difficult to get a lot of qubits together. Depending on what problem you want to solve, you need to look at the hardware's advantages and disadvantages. Because I don't have that much time anymore, we will go to access to quantum computers, which I think might be most interesting for all of you. So yeah, quantum computers are located in research labs, and you can connect to them via cloud access. There's some on-premise solutions, different HPC quantum labs also integrate quantum computing. You can access them via Amazon bracket. So it's actually everything that you're used to. And also in the future, people are also thinking about having a quantum computer right next to them so you don't have latencies. Yeah, so all you have to do if you want to code on a quantum computer now is think of an application, formulate your problem in a way that a quantum computer can read it, which is dependent on the type of quantum computer that you use. Then you just map your problems onto the qubits, write your algorithm, and then send your circuit to the QPU, whichever QPU you choose. And each QPU has different properties, you know, different number of qubits, there's different connectivity between qubits, and you have different operations that you can do, and a different coherence time or fidelity. It's really dependent on the hardware that you use. That's why if you want to start with quantum computing now, you should be aware of the hardware that you use. We can definitely go deeper into this in further talks. So yes, I told you everything is linear algebra. So I will just show you this one example. So you have your qubits that you initialize, and then you apply gates to it. And applying gates to it is basically just matrix multiplication. So you don't have to repeat what you learned in linear algebra, but that's just the entire magic about it. And I'd like to show this so people are not too afraid to jump into it. It's not something mystical, it's math. Yeah, so today we are in the NISQ era, which means we have small number of physical qubits, they're very susceptible to noise, and you can only use them for specific applications. But they have demonstrated quantum advantage for some problems. So we still need error mitigation strategies. What we're hoping for in the future is fault-tolerant quantum computing with large number of physical qubits, so we have a sufficient number of logical qubits, right? So we already have the error correction. And the quantum advantage here is expected for many problems. And this is still an early stage development. There is no access to a real fault-tolerant quantum computer yet. And once we're at that stage, then you don't need to care about the hardware or the platform. And there's also some companies that will give you software that has a compiler that does most of the work for you if you know how to formulate your problem. Yeah, and then there's different algorithms, just like there's some classical algorithm as well. There's algorithms for NISQ, but there's also algorithms for fault-tolerant. The RSA encryption, why I say it's not a threat yet, actually needs a fault-tolerant quantum computer, which is just factoring large numbers. Grover is the search algorithm. So I have 3 more minutes. I just want to briefly do a live demo. So remember when we talked about entangled states. Okay. So when we talked about entangled states, we can show them with Bell states. That means that we connect the 2 qubits with each other, right? So we can actually build that entangled state for 2 qubits, and to show this, we can use so-called Bell states. And what I basically did is I built my circuit. As you saw in the view, I have 2 qubits, and then I have a classical qubit to read out my result, right? I think maybe I'm not connected to the internet. Oh. Of course. I need to choose my sampler. And what I'm doing here is I have my 2 qubits. I initialize them with a 0. Then I need a Hadamard gate. This gate you will read a lot about. This Hadamard gate, all it does is take your qubit and put it into a superposition that is 0 and 1 with the same probability. And then I want to connect my 2 my 2 qubits. Can you see my mouse? Oh yeah, great. I want to connect my 2 qubits with a C0. So now they are entangled. And then when I measure them, they get only 2 results with the same probability. To visualize this a bit more, I have here. I have the following view. This is actually accessible through IBM. Qiskit also has a very good entrance documentation. I don't work for IBM, so it's no advertisement, it's just the truth. And you can use 5 qubits for free and then run it on a real quantum computer, but you're like set up in a queue. This can take everything from 1 minute to many hours. I recommend you do this late at night, like 12, 1, 2 a.m. There's literally no one running code on it. But at this time, lots of people are running code on it, so don't really recommend you do it at that time. But what I actually want to show you is you have this inspector, which I will turn off. I will go to my first qubit. I will turn it on, and I will show you what happens. So when we start, we have the initialization at 0, 0. Now, I go to my next layer, which is the Hadamard gate, which puts it into the superposition. So now it's in this mixed state of both 0, 0 and 1, 0. Now I connect my 2 qubits, and then it has the probability of 50% to be 0, 0 or 1, 1. It's the first Bell state. Okay. But what I really want to show you, so this is the result when I use the simulator. It's the perfect result, 50% 0, 0, 50% 1, 1. But what do I mean with quantum computers have errors? So this is the result when I run the same example with 1,000 shots with a quantum computer. And you see, yes, 1, 1 and 0, 0 has the majority, but there's still some errors. 39 occurrences were 0, 1, and 40 occurrences were 40 occurrences were 1, 0, which is not allowed. So we have errors. That's why we run the same code multiple times, and then we get a probability. That's why when you talk about quantum computing, we say it's probabilistic and not deterministic. But the advantage of that is we can actually have real random numbers, which we don't have right now in classical computing. And yeah, that's it. So now I think it's still time for questions.